Today, we are continuing the construction of a centrifugal pump or a turbine. The way to construct, it's the same method to construct both of them because one is just the reverse of the other. Exactly the same components, blades, impeller, volute, and some mechanism to just join them together. You have either your turbine or your pump. Now, it is important for us to understand the theory of assembly in CAD programs, especially in FreeCAD. The theory is similar in whatever CAD environment you work with. So today I will show you examples in FreeCAD and in Fusion 360, where my examples are far better developed. But the reason why I'm showing you the Fusion 360 one is because even though Fusion 360 is a little bit more polished than FreeCAD because it's a paid-for application, the logic is essentially the same. I like FreeCAD because it is free and it is growing. So I'm not looking at FreeCAD as it is today. I'm looking at the way FreeCAD will be 3 or 4 years down the road. It will likely be as good or as supported as Fusion 360. It is not yet so. But at the same time, it is free and we can do most of what we want to do in it. So you see, this is the kind of thing we want to do. But I want to do the assembly on the right. The reason why I'm bringing the assembly on the right is that all the issues of, most of the salient issues of assembling a product, you will come across virtually all of them in the way we build a very simple model like the one on the right. So once you understand how to assemble, we go back again to the turbine and the other things we want to do. But I'm just using this to teach the theory behind assembly and then have some practical experience using it. So today's goals. We are to understand how to properly organize a drawing to obtain an assembly. So the proper organization of a drawing to obtain an assembly. You don't just draw anyhow, and then at the end, you now say, I want to assemble the things. It's not going to work well. You know ab initio that you want an assembly. So you begin to plan for the assembly top down. You have an idea of what you are looking for. Even your first sketch is not reflecting the first thing you want to make. It's reflecting the total landscape, the landscape plan of the assembly. Assembly arranges components of parts to enforce kinematic relationships. That's a mouthful. What do we mean by components? What do we mean by parts? And what is the enforcement of kinematic relationships? What is kinematic relationships? Look at kinematics as geometry. There is, for instance, you talk of putting the cart before the horse. Now, if you put the cart before the horse, it's not going to work well because the horse is supposed to be in front of the cart. So that arrangement is necessary for you to be able to have correct motion. Similarly, if you are on a bed, you are on top of the bed and the bed is under you, not the other way around. And then you do not enter the bed. But if you draw anyhow, you will see that you can have two drawings and you can move them. And when you are moving them, they are passing through each other. That kind of drawing is not realistic. You are just trying to force some realism into your drawings so that if any of your bodies will move, they will move in a way that mimics what happens in real life. For instance, you will not have a motor car that passes through a wall. That's not going to happen. A motor car can crash into a wall, but it's not just okay, unless you are talking of films and some other tricks. But in reality, a motor car cannot pass through a wall. You cannot walk through another classmate of yours, and you cannot pass through your door. So all those geometrical relationships are what we mean by kinematic relationships. They are kinematic because we are not just looking at the static geometry. It involves both static geometry and dynamic geometry because when the objects we are talking about are not all fixed, so you are now talking of kinematics. You are talking of the way they continue to relate to each other geometrically, even though some of them are in motion and they are not static. So we will explain what we mean by components shortly, and we will distinguish components from parts, and we will distinguish parts from bodies. It is important for you to understand these differences for you to be able to do well in the idea of assembly things. Where, like I said, you are prevented from moving parts through other bodies. Now let us look at other things we'll do today. We will take a look at master sketches and parametric design. You will have a sketch that you are not going to use to do anything other than to guide other sketches. So they are master sketches. They are master over other sketches. It's not because you want to draw anything or you want to make a body from them, but you want to use them as a template for other sketches. You will get to see why such master sketches are needed. And you bind shapes to master sketches. So even though a shape may have its own sketch, but somehow that shape and that sketch is related to the master sketch. So that if you make changes in the master sketch, there will be some consequence in the other bodies that depend on that master sketch. And because you can therefore propagate changes through, you can in this way propagate changes through the entire assembly. So you can change something in the master sketch and it will reflect in the entire assembly. So let us say you change the size of a pin, and there's a pin connecting the piston uh, with the crankshaft and all those ones. All these things, once you just make a change there, you see that they all adjust to make the drawing still reasonable and coherent and consistent. So those are the things we want to achieve in today's goal. So if you find us not achieving any of these things, you can raise the question, and then if I need to go through it again or to make some discussions on it, I will do so. Hierarchy of drawing entities, forming an assembly, and enforcing kinematic relations. We will talk about sketches, which we have been doing, bodies, which we have been making out of sketches, but we are going to introduce the ideas of parts and components. And then you will see what can be assembled. That is not assembles. What can be assembled? You see that bodies and other solids cannot be assembled on their own. They must become a part before they can be assembled. So you will distinguish between bodies, parts, and from components. How to set simple how a set of simple drawing can create a useful assembly. Note, today's FreeCAD drawings are done in FreeCAD 1.1 release candidate 2. FreeCAD is very floppy in a way, because if you use one version of FreeCAD to do something, you may find out that even though the drawing will still work, but the menu arrangement and several things may have changed. So for you to use what I'm discussing today, I built everything in FreeCAD 1.1 release candidate 2. You can find it, you can download it from their website and install if you need to, so that you will not be having the heartaches of not seeing what I say you will see when you are trying to do your own drawing. You may want to update your local version by visiting the FreeCAD website and getting this latest version. It is not fully stabilized, but has more coherent features. And one of these is a specific assembly workbench. In the other versions, you can have different kinds. There is assembly 2, assembly 3, assembly 4, and they're all different ways to assemble things. I think that's a bit confusing. In the FreeCAD, the latest version of FreeCAD, there's only one assembly workbench that is supported. And that's a very good assembly workbench. It's just called assembly. So the master sketch. A master sketch in FreeCAD is a single controlling sketch. It defines the key geometrical relationships for multiple bodies, like overall dimensions, lengths, offset, diameters, reference lines, points, axes, and functional relationships like datum planes, spacing, symmetry, angles. All those things can be defined in in the master sketch. And we will do a very simple master sketch that you will, because if you do not understand the theory, when you actually go down and get your hands dirty doing something, it may teach you more than you hear with the ear. What you do, you learn more from what you do than what you hear. So even if you are not understanding everything I'm saying, just wait until you start doing it. When you start doing it, it will come naturally when you succeed. And for you to succeed, I will provide some helps. I've been providing some helps in videos, but today I'm going to use a different method. I will see whether that method will be superior to the videos. So the master sketch is not designed to create solid geometry directly. It exists to drive other sketches and features. Uh, so the typical location is inside a dedicated skeleton or master body. It's a body that is just an abstract body which doesn't create anything, but just to hold the master sketch. And it relates to other bodies through a facility called shape binders. One of the things you will learn today is how do you invoke shape binders. So when you invoke a shape binder, let us say you have 6 or 7 components. Each time you invoke a shape binder correctly in the component, you are connecting that component to the master sketch. And the things that are uniting them, once you change them in the master sketch, the shape binder will enforce that rule in the other in all the components. Well, now, I always like to refer, I always want us to know why we are doing what we are doing. Even though this is a beginning course on graphics, and you are not yet advanced in your education at the University of Lagos, there are still a long way to go. But I want you always, even though it's just a course in drawing, the drawing is not just drawing for joke. We are drawing so that we can make a difference. The centrifugal pump, for instance, that we are looking at right now, is found everywhere in Nigeria. But I'm not sure if anybody manufactures them in Nigeria. How many of it do we buy yearly? The question is, why don't we manufacture them in Nigeria? Where we are bringing them from, are they made by angels or is it human beings like us? I want you to begin to ask such questions, and that's why I want us to bear that in mind when we are looking at the anything we are drawing. I took a picture of your sisters or my sisters, the way they labor to get water. The whole idea of engineering is to prevent this kind of sins. And the more we see this type of things in the country, the more we see that our engineering is failing. Uh, so just mark that. And then I want you to watch the video. There's a video link here. If you watch that video, it will show you how a centrifugal pump works. You can go to the web yourself and we can see hundreds of videos about such things, but I'm just giving you one in case you are too lazy to go and search for yourself. It is a good idea so that when we are drawing it, we are designing it, and I want you to know how it actually works. Uh, the turbine is the same components as the centrifugal pump. It has a volute, it has a impeller, it has pipes, and they are all doing things in reverse. So the one that will be the inlet for the centrifugal pump is the outlet for the turbine. So whereas you put power in the centrifugal pump so that it can pump water, in the case of the turbine, you put water that is flowing in a turbine so that it can generate energy. So it's like a generator. So, like I said, the engineering training is supposed to prevent sins like the one you see on this page. So bear that in mind when you are studying. We are not studying centrifugal pump or turbine or anything just to get a first class. It is to prevent this type of sins. So we go back again to the volute that we have seen before. I gave you assignment and I told you to do some Boolean arithmetic with some things to be able to get a volute that should look like what I have on the right-hand side. I just showed you 2 views of it. Essentially, a volute is a hollow metallic vessel with decreasing spiral shape or increasing, depending on which direction you are starting from. If you start from the big end, it is decreasing. If you start from the small end, it is increasing. So it is changing spiral shape and that ends in a protrusion as shown. So it will be increasing to that straight line or decreasing to the curved line. So whichever one you look. It is open at the protruding end. The inner part of the spiral vessel is open to receive a cylindrically shaped rotating part, chiefly made up of the impeller. The rotating part is simply chiefly the impeller. There are other minor things that are there, but the main thing in the center is the impeller. So once you have done the volute, the next item on the agenda is to know how to do a proper impeller. The volute is the passive or static part, whereas the impeller is where the actions take place. There are many other possible ways to shape a volute. What we have been handling is a basic type. So once you understand the basic type, then you can go to town and do other things. I want to quickly remark that a volute is not the same thing as an involute. I did that because in the previous set, it was too late for me to correct it because in their exam, in their homework, people misread it because those two words are very close, but they are very far from each other. A volute is a spiral-shaped casing whose cross-section gradually increases or gradually decreases. And not only so, and it is it's something like looks like a circle, but it's never a circle because the cyclic radius is always changing. So that is a spiral object of increasing thickness or increasing radius as it goes. Uh, whose cross-section gradually increases or decreases depending on where you are starting from. And it is wound around an impeller or rotor. It's a three-dimensional functional shape. It's not just a curve. An involute is a mathematical expression, and it is a precise curve defined as the path traced by the end of a taut string as it unwinds from a circle. So if you wind a string on a circle and you keep that circle fixed and you are now releasing the end and you are going around, making sure that the string remains taut all around, what you get there is a curve called an involute. Involutes, the path traced by the taut string is called an involute, and it is one of the things they use to form, one of the main things they use to form the gear, the teeth of a gear. There are reasons why that is so, because when two surfaces mesh in an involute, there is a way that reduces the amount of stresses that you are going to get so that your gears can last long. So as engineering students, understand that a volute is not the same as an involute. We are here discussing volutes. I hope you have handled the volute. I'm not sure if I gave you the code to do a volute or you have submitted the assignment of doing the volute yourself. I will see when I get the assignments that you submitted. The impeller can be as simple as a round disc here with three teeth, for instance, that are simple extrusions. In fact, I am sure I will be surprised if there's anybody in this class that cannot do this. It's very simple. This is perhaps the simplest ways an impeller may be shaped. It can be as simple as this. The blades can come in a variety of ways, numbers, and variableness. So the blades here are 3. You can have an impeller with 7. You can have an impeller with 25. And then you can have an impeller that has more than a single type of blade that has more than one, usually 2. I've not seen one that has more than 2 different types, and they are interspaced for several reasons. We will talk about that later. The disc is usually attached to be moved by an engine or pump to drive a shaft turbine. It is obvious that the shaping and orientation of the blades will affect the way the pump behaves. So what we are going to do as engineers are always concerned as to how they shape the blades and how much fluid it can pump as a result of a particular shape and how much power it can generate in the turbine of a particular shape. So you are trying to see how to optimize the blade shapes to give you the best results. Those are the kinds of things you want to do. It is obvious that the shaping and the orientation of the blades will affect the way the pump behaves, how much pumping you can do, how much fluid you can move, and then the power of a turbine. If you give it a particular amount of flowing water, how much is it going to how much is it going to yield? How much power is it going to yield? If I had two blades, if I make it three, at what point would the law of diminishing returns occur? For instance, I'm sure you already know that in a fan, you can have a fan that has two blades, you can have a fan that has five blades, but why can't you have a fan that has 100 blades? There's a reason. You might be wasting your money on blades because there's a point at which increasing the number of blades will not give you a better behavior. Those are the kinds of things that govern the engineering of these things. So the first order of business, as we have done before now, is to get the spine of the volute. It turned out to be more difficult than I had expected. The problem is that FreeCAD does not provide you a spiral primitive in its base, but you can have it in FreeCAD. And those of you, uh, apart from downloading FreeCAD, you can also download the Curves Workbench. If you download the Curves Workbench, there is free spiral there. So you can take a spiral without needing to program, or you just tell it what is the initial radius, what's the final radius, and you just give it the parameters. Okay, so we talked about that. And then I will first of all have to look at your responses in your homework to see whether enough of you succeeded in making the basic volutes and so on. You will know that you will need a loft to a second time to create the hollow, but we'll talk about that one later on. Let us just move on. So, like I said, all you need to do is to just create two circles and then draw the shape of the blade you want. And then if you have drawn it correctly, you should be able to pocket, no, not pocket now, you should be able to pad, and these things should be created. I mean, you can even make a very crude blade. You can make it straight, and then uh, you use polar pattern replication to get many. So once you do one blade, polar patterns can create as many as you want. So you are not supposed to create more than one blade. If all the other blades are similar, if there are two, then you create two blades and then let the others be similar. But you are not supposed to do anything more than that so that you can create the polar patterns. Making impeller comes down to blade design. The simplest is a simple circle extrusion with the extrusion of 3-point doubly offset. FreeCAD does not allow you to offset open paths. So I don't know. You might be able to do this a little bit manually or use some other means to do the shape here, but it can be done easily. You can decide how many blades you want by creating a polar pattern of them. So when we put the impeller inside, we get the picture you see on the right there. And when we make a cover on top of the impeller, with the pipe coming in, you get the picture on the right. So we make the covers to the front and back and proceed to assembly using a rotational joint between the impeller and the volute body. Notice the elongations for water intake and water outflow. Those elongations are necessary when we are doing analysis, because we can only analyze fully developed flow. So those things are not exaggerations. You have to have, in a real turbine, it won't be like that. But in an experimental turbine, in an analytical turbine that we are interested in, we have to project the ends for our simulation and design. So a simple engine in FreeCAD. Like I said, even though our interest is to do the volute, the impeller, and the turbine or the pump, we digress a little bit. And in this bit, we're going to go through a little video. I have linked you to a video where you can get a very simple set of 6 objects that can be assembled. All what you learn in assembly there can now be carried over to how you do your assembly in the volute. It will be easier because this simple thing has a lot more nuance than just assembly. Because in a volute and impeller, you do not have more than 2, 3, or 4 maximum different objects to put together. But when you are looking at a motor car engine, you can easily get 50 objects you are trying to put together so that they can work synchronously. So that usually gives you a much bigger challenge for assembly than what you are doing. So when we start, no matter how simple it gives you the salient parts of the assembly. So this YouTube video is very simple. I have my own drawings are far more complex than it. I will show you some hints of my own implementation of the same drawings. But what I like about it is that, see, it is so simple that it allows you to concentrate on the real issue of assembly without getting lost in the complications of the engine part. That's why I like it. So the website, the web page of the video I've given you, I'm giving you. So once you get my slides, you will see the web page. And that's the simplest part cases. Don't be misled by the simplicity of this. All the parts there are either a simple extrusion or a simple revolve. But the issues there are very fundamental and are very useful. The good thing about this clip is that the parts there are either a simple extrusion or a revolution of a simple line, or about a simple line. Attention is therefore on the assembly issue. I implemented the data and most of the steps in the video. When I went through the video, I knew that just giving you the video, even though it looks simple and the author makes it so simple, it's so easy to do. But it might take you time for you to get it. So I decided to draw it myself, and I will share my own drawing with you. But sharing my drawing with you is not supposed to make you lazy. It's supposed to make you faster. So even whatever you don't understand, you will see it has been implemented and you can see it. And I'm hoping that you will take that advantage and use it to learn and not be lazy and then say, this has been done. You don't need to bother. Please bother, because the way I set exams is that I give you half-baked graphics and I tell you to fully bake it. So I may do something that should take 50 minutes or 60, that will take 1 hour. I may do the first 50 minutes and say, okay, given this thing now, finish it up, do this, and this. If you have never seen that drawing before, you have never done it before, you will not be able to do it during the exam stress. And even in exam, you are still going to draw. So yeah, I'm not going to ask you theory question. Okay, distinguish between a component and a body. Which one then? How do you use a component and body in an assembly? What is the use of joint? Know all those things in the way you use them. Don't know them thinking I would not ask you to be telling me. You're not going to tell me any stories. You are going to, if you know them, you are going to put them into practice. So every drawing I give you, every example I show you, you are bringing everything in your file to the exam hall, and I can call upon any one of them, and I say, okay, since you did this, okay, finish it with this or this. For those who know what they are doing, 5 to 10 minutes, maximum 15 minutes is all they will need to get the answer I need. For those who don't know it, even if you give them 3 hours, they will not be able to do it. And that is why there is nothing unseen in the exam of this course. Everything you are going to be asked are models you've already played with. So please bear that in mind. So this implementation here is my own file. So it will lead you to my hard disk on the web, my OneDrive, and you can download the drawing I did in FreeCAD so that you can use it, and then you can now improve on it and use it to, and then do it on your own. And then you can now begin to do better things than that because I've given you that kind of advantage. So there are 2 changes I made from what the guy on YouTube did. The slider motion, I don't like the way he created the slider motion. It's too difficult. There are much simpler, much better ways to create slider motion. So I used a better way to create the slider motion. And then he didn't put any pin between the crank between the connecting rod and the piston. And I think it makes things difficult. If you put one more object, it makes the drawing and the design very, very easy. And this is what you will not, okay. This is the master sketch for this particular drawing. The master sketch is a drawing that has essentials of the entire assembly, especially where different components intersect. You begin each body from the master sketch, in the sense that it is the master sketch that you use to create your own sketches for everybody. May add more graphical elements in each body, but the essential unifying parts are in the master sketch. This makes the drawing parametric in the sense that changes are reflected in all parts when they are made in the master sketch. This sketch is my own implementation and equal to what you have in the Mango Jelly video clip that I'm giving you. Additional component. Here is the pin inside the piston, an easier way to implement that joint. It's better to implement the joint with a pin than to implement it in vacuum. The other figure, the other thing I introduced is the cylinder. So you see the things that are in my drawing are stator, cylinder, piston, pin, connecting rod, I think crank. Yes, there are two cranks. There are two aspects of the crankshaft, which are called crank 1 and crank 2. And there are several joints. There is a grounded joint, there is a fixed joint, there is a slider joint, there are 3 revolute joints in the drawing. And 2 grounded joints. Oh, no, there are 4 revolute joints, 2 grounded joints, and 1 fixed joint. We will get to know what those things are as we move on. And let me see whether you can hear this an old 4-minute video clip that I made maybe 2 or 3 years ago, but it may still be relevant for your assembly thinking. So let me just play it. And then if you, it is just going to last for 3 minutes or 4. And I will just be quiet or even leave the room. After 3 minutes, I'll come back. If you hear it, fine, I will move to the next thing. If you don't hear it, I can describe it to you. Just take your time and watch this. The picture here shows the connecting rod that we have made, and I'm hoping that everybody in class can replicate this, which is actually 2 components now, the head of the connecting rod and the connecting rod body. You will notice that the big end of the connecting rod is in the cyclical motion, and the small end is in a reciprocating motion. That is what we get at the end of these drawings if we want to create a real 1-cylinder engine like we will do. And in order to look at that, the reciprocating, the rotating motion is caused by the crank. And let us take a look at the crank and how it works with this now. Take a look at the crank here. The crank here creates the rotatory motion, and you can see how the crank rotates. And so that's, in this particular case, we created the crank as a single item, both the 2 holding sides as well as the big end for the connecting rod. Everything is here created as a single object. I would explain how this assembly was achieved shortly. So as a result of the creation of the piston, we can show you how the piston creates the reciprocatory motion at the small end. So let's take a look at the piston here. And you can see the piston here is reciprocating while the crank is creating the rotatory motion. And how do we get the piston to reciprocate? We get it to reciprocate by forcing it to slide through a cylinder. Now, this is an example of a cylinder. So with that cylinder, we make sure that the motion in the cylinder is sliding motion. And to anchor everything to a fixed, non-moving engine, we now have the engine block itself, which is holding the 2 sides of the crank in a way just like this. So you have the full engine in motion like this. And our objective in today's lecture is to take these components one by one as we have created them. And we are going to show how these motions can be simulated or can be animated the way you are saying it. And the only two things we have not yet created are the stationary parts, which is the block here, the block below, and the cylinder on top. We deliberately didn't make the cylinder too long so that you can see the piston as it enters and goes out. In reality, most of the motion of the piston will be wholly contained inside the cylinder. Uh, Please, may I ask, can people in class respond? Did you hear the words? Was it clear? Or do I have to explain what was just showed? Let's see. Okay. So you had it. Okay, good. Good. This is where we are going to, we will soon go for our break, but this is what I'm going to do. I want to show you some of the abstract terminologies we use we will be using in FreeCAD, can be seen here. First of all, know that the word joint does not mean anything physical. So in this picture you are looking at, there are at least 4 or 5 joints. So let me just show you what joints are here so that you can know what we mean when we say joint. For example, the block part that is in purple is, is in what we call an immovable joint. That is, it will never move. So it is fixed to the earth, fixed to the world. In the case of a car, it will be fixed to the car. The car is the world as far as the engine is concerned. So anything that is fixed to the car is that it is not moving. It's only what is moving relative to the car. For instance, you know that the tires rotate with respect to the car, but the bearings that are carrying them will not rotate. Similarly, the engine block is fixed with respect to, so this, all that kind of thing will be represented by what we called a fixed joint. You can't see the joint, but the technical way, every a graphical package would call it, is that it has an immovable joint. So it's an immovable joint. So that is the things that are immovable, that are things in this case that are fixed with respect to the earth. Now, the next thing you see are the rotors of the crankshaft. The rotors of the crankshaft, they can rotate on that thing. They can rotate. So because they can rotate, they are said to be in a revolute joint. There's a revolute joint between this rotor and this immovable, because this thing can rotate around here. Now, but the rest of the crank is fixed. It has a fixed, it's in a fixed position. They are fixed with respect to each other. So you either take them as a single object or take them as a multiple objects that are fixed with respect to each other. So we have talked about 2 joints now. One joint is the immovable joint. The second one is the revolute joint. The third one is the fixed with respect to another object. So you have revolute. Now, the third joint is the slider joint. You will remember that this piston was going up and down. It was going up and down. No matter what happens to the others, it's only the only motion permitted is that it is going up and down. And inside the piston, there is a pin that is holding the piston to the connecting rod. That it is fixed with respect to the piston and the connecting rod, allowing only some revolute motion to occur between the connecting rod and the pin. So you can see the number of joints, even though you are seeing a very simple picture here, there is a number of joints that are involved in this one. So uh, we are 2 minutes to 11 now, but I want to just show you one more thing before we go on break. Let's see. Okay. So after making a single engine, sorry, a single cylinder, we can actually replicate it and make more cylinders. And let me just tell you what now is different. This video should not play for more than 3 or 4 minutes. So let us just play this one. We can talk about it when we come back. And then we'll... The 6 cylinders assembled are as shown in the picture here. We can animate them by just simply going to one of the revolute joints that we did before and animate the joint relationships. So the higher is the cylinders that we have just assembled with as built joints. And if you want, you can use something like this orbit tool to see this thing from different directions. You can look at it from the bottom, from the top, upside down. This is what you get. And then we can then take it back to the home. Let's see, we take it back home here. So that is what you have. The assembly of each cylinder is the same process. The only thing that distinguishes one cylinder from the other is the firing angle, which we computed in an earlier slide. So once the firing angle is correct, then you rotate statically to that firing angle before you do your final rigid connection between the parts. And you can see, if we stop this motion, one interesting thing is that it is the firing angle that dictates the way our crankshaft looks. We can take off everything except the crankshaft. What we can do now, we go turn off this, turn off the joints, turn off, so we can start by turning off everything apart from the crank. So in the number 1, we leave the crank alone. We turn off the block 1, connecting rod, and piston, and cylinder, and this, and this. And then we do that for block 2. Turn everything off, except the crank. Turn everything off except the crank. So if we take the origin off also. Okay, so you can use an orbit to look at it now. Here is a crank for this particular firing order. If you have a different firing order, the crank's orientation will be different. You can also continue and use the joint to see how the crank alone moves. So if we go to the joints and we do an animation of the joints, the joint relationship, this is how the crank will move. And if we go home, one thing you will see is that the rotor of the crank is almost, the rotor of the crank is connected to a fixed part of the engine, and you can see it does not, it only rotates, it does not move. There's no motion along the rotor of the crank, but it is the big end, the big pin of the crank that moves the crankshaft and move the connecting rod and the piston. So this is what you get here. Okay, so let us go on a 15 minutes break. I will see you at 11:20 to finish the class. Thank you. So I hope the class is back. And now let us just look at what we have done here. You can see that the drawing, for instance, of this crankshaft looks very, very complicated, but it is just like 3 pads and 5 revolves. All that is there is just the assembly joints that will make them look like this. And if you change the firing order, it will be a different type. And you can see that you can get some things that look very complicated are done with very, very, very simple very efficient methods. And that's what I want you to see as I show you again the last part of this video here.
Firing order. If you have a different firing order, the crank's orientation will be different. You can also continue and use the joint to see how the crank alone moves. So if we go to the joints and we do an animation of the joints, the joint relationship, this is how the crank will move. And if we go home, one thing you will see is that the rotor of the crank is the rotor of the crank is connected to a fixed part of the engine, and you can see it only rotates, it does not move. There's no motion along the rotor of the crank, but it is the big end, the big pin of the crank that moves the crankshaft and moves the connecting rod and the piston. So this is what you get here.
Okay. Okay, so I hope the foregoing demonstrates clearly that it is better to create several simple parts for an assembly than to make a complicated part. That is the point I'm trying to make. The assembly is the real deal. So if you know how to assemble, you can always get all those primitive parts from other sources and put them together. That is more important than even making those parts themselves, though everything you should be able to do. We shall therefore concentrate on the parts of the centrifugal pump, the volute, the impeller base, the impeller, and the inlet cover. All of them, apart from the volute, that is a bit technical. The others are very simple parts. It is straightforward to assemble them if we do things right. We can also assemble them parametrically as described in the YouTube single engine master sketch. Polar patterns of simple blades. For instance, this is an example of a slightly more complicated blade, impeller than we saw earlier. But you see, to create the platter, which is just a small, it's very thin cylinder, it's very thin cylinder with very small height. That's all. And then you make a blade profile. In this case, we still choose a simple blade profile, which is essentially the thickened arc of a circle. And then once you do that, you then go to pattern replication. In pattern replication, once you start with one, you can create several. That's what this should be easy for everybody. Now, I'm going to ask you a very genuine question at the end. I want to know people who are struggling with some things because there are some few things I want to do between now and before we end the course so that I can carry people who have not been carried along. You tell me because some things I assume are very easy. If they are not easy for you, say so. Uh, Here you have this pattern replication here. And then after the pattern replication, we just created an additive revolution on top of the plate, which is we just made a profile and revolve it around the plate, and it just filled in the rest, and that's what you get. So from here to here, from here to here is pattern replication, polar pattern. From here to here is simply a single additive revolve all around it. That's what. So this may look so much more complicated it may look so much more complicated than the single blade, but it isn't. I'm also sending you, I think, I'm not sure if I gave you the full file here, but I gave you the full file of even a more complicated thing than this. So let's see what happens next. Here, you are having a very complicated blade profile. In this blade profile, again, the workflow of this blade profile is given to you. The whole file is given to you. So this is the blade profile. So, and we use the helix object in FreeCAD to do this. And I gave you, I'm supplying to you the entire file that I used. So you will see how we created a single blade and how we now replicated that blade to become many blades. We can combine the same workflow above with a helical blade that curves and slants in a variable fashion as dictated by the parameters we select for creating helix, for the creating helix. The procedure is the same. We determine how many blades are needed and obtain the profile from a polar pattern. So this is actually this the these are the form you will fill to get that particular profile. So once you change this pitch, you change the height, you talk about the tones and angle. Once you just give this, it will give you a different profile if you change that. The additive helix parameters. The parameters of the additive helix blade are as shown in the picture. The base blade profile on the platter can be a simple thin rectangle or slightly curved middle shape that we offset. FreeCAD does not appear to facilitate an offset of open profiles. We may do this profile manually or by using a Python code. So this is a case now where I've made a pattern of six replicas of that blade around the circle. That's what you see here. We can create something in the middle there. Here, it will be necessary to create the central attachment and turn and also trim the top of the blades into shape using a subtractive revolution. So you can use additive revolution or subtractive revolution to do some of this. But I gave you this full file. You are getting the file so that you can play with the file and see things that I cannot show you that easily in class. So the engineering questions. How should the blade be shaped? How many blades should there be? How tall and wide should the impeller be? Those are the questions that determine what kind of impeller, turbine, or centrifugal pump you are going to get. And that is actually the question, that's the question you are trying to answer by being in a university studying engineering. How do you answer those questions? How should the blade be shaped? How many blades should there be? How tall and wide should the impeller be? That is what is called design. You see, you are designing on what basis? You are doing that to check what will be the best shape that blade will take that will give me the best performance. If I'm to generate electricity with a turbine, given a particular height of a river and the particular flow rate, how can I shape the blade so that I get the maximum amount of power from that turbine? Those are the things those are the questions that an engineer asks. So you ask such questions, and then where do you get the answers to those questions? Where are these questions answered? The engineering simulation is a combination of several courses you take in design. They are combined in software. It can be mechanics of fluids, mechanics of solids, thermodynamics, heat transfer. All those things are combined in design software. And what the first step is to have an actionable graphical description of a pump or turbine, not a photograph, but a parametric drawing in which you can modify the blade shape, the blade orientation, the number, then the impeller, the volute, and so on. When you have that, you now put that in the simulator and you begin to change all those things. You have not made anything, you have not designed anything. You can test 1,000 different possibilities and then have maybe 2 or 3 that are promising to go and now make a prototype of. That is what is called engineering. So what we do is this is how the simulation goes. This is an example of a simulation in what you call Autodesk. This is Autodesk. What is the name now? Autodesk CFD. That is the software we use to do this. So you must fill inside the turbine, and the one of them must be full of fluid, and then you now set all your parameters. You run the program, and then you keep changing the sizes of the blades until that is the reason why we are doing drawing. We are not just doing drawing because it's a very nice thing to be able to do drawing. Of course, you can do other things. You can use it to be a graphic designer, graphic artist, and you can make your money and your bread there. But the reason why an engineer does it is one of the reasons is to prepare models for simulation. So this is what I am just trying to let you see, that our goals might be different, from the goals of other people who are using the same uh, thing. Okay, that's the end of this set of slides. I have another set of slides to show you and to discuss with you, but I want us to have a frank discussion in class, and that what the result of that discussion is going to guide me into what I will do for the few lectures that we have left. So I want you to let me just see if I can. If please, can you all go to the chat room and answer me from there? Are we still on? Is the okay? Yes, I'm trying to get to the chat room. Okay. Okay. Now the question I want to ask: are there people in this class that even the simplest of what we are doing is quite difficult for? Are there people? I want to know how many people we have left behind. Are there people that are just struggling? For instance, I said it should be easy for you to do the simple extrusion on a plate. Are there people that find that difficult? And what if I send you a video online? How many people have fundamental difficulties? Let me know specifically what problems you have, because there is one thing I want to change between now and the end of the class. Ile Mobade said, yes, there are people. Please, can you finish that sentence? What can you say about yourself? So don't. Uh-huh. I said, yes, sir. I don't know. Can you be specific? What problems do you have with this course? Can there people having difficulty with basic skills? They cannot do a simple sketch. Are there people struggling? You cannot create a sketch. Tell me if there are people who cannot create a sketch and draw a circle. And there are people in the class who cannot create a sketch and draw a circle. There is a reason why I'm asking this question, and I'm not still getting any answer that is satisfactory. I want to know where you have difficulty. Are there people who don't understand the videos that I've sent? Are there people who cannot use the videos or the things I've given you to productively improve their ability to okay, you can draw. Okay, good. No, because if there are people who cannot do something that simple, you can draw a circle, you can pocket it and you can pad it and get a cylinder and such things. So basic things are okay. Okay, what I'm going to do for the rest of the class, I want to take you through I'm sending you a video that I saw on the web. I want to take you through that video, and I will not do another video. Instead, I'm going to write out all the simulation can be done in FreeCAD, yes. Even though the simulation I did there, I did it in Fusion 360 several years back. Sometimes you describe a particular diagram, you describe, okay, good. Ilimobade is talking. Sometimes you describe a particular diagram to be easy. When it is carried out, it can look so tough. But I guess we need more practice to overcome this. Also, some fundamental tools in FreeCAD I find difficult to navigate them easily. I believe we can make sketches, but there are problems we face when trying to constrain everything, and also some icons on your free card are wired differently from my own version. Well, the second problem will be answered. Please just go to the latest version. And I will only be using the latest version now, even though it has some bugs and errors. The other question that some things look so simple, and then when you try to do it, they are tough. I'm sure you find that with all the people talking on the web. They say, oh, this thing is easy, just do like this, just do like that. And if you try those things, you just discover that even the people doing it, they are lying. They didn't, it wasn't that easy for them. But by the time they finally did it, they can now be telling you that it is so easy. So don't be overwhelmed by that. That's how people do. Once something is clear to you, The latest version isn't open to the public. It is open to the public. What do you mean that it's not open to the public? Go there and download it. It's free. Ali, go there. It is open. I have downloaded it for Windows. I've downloaded it for Linux. I've downloaded it 4 times. So I have 4 installations of it. So it's available. That is it is the 1.1.rc2. Sorry, 1.1.0.rc2. Really, it is called the release candidate 2. It is version 1.1.0 release candidate 2. It is open for the public. So there are also problems with FreeCAD itself. There are times when FreeCAD ceases. Aha, yes, Ayomide, that's it. 1.1.0.rc2. I experienced bugs in the older version. Even in the new version, there are still bugs. Don't forget that this software is being developed by volunteers who are not being paid for it. So they are just doing it out of passion. But don't think, therefore, it is going to be inferior to the ones you pay for. If you think so, compare Wikipedia to Encyclopedia Britannica. Wikipedia is completely free and it's being done by a lot of people that are just hobbyists. But that's the best encyclopedia in the world. It did not start out like that. When Wikipedia started, people were laughing. Nobody believed when Wikipedia started that it would be even 100 as good as Encyclopedia Americana or Encyclopedia Britannica. But now it has surpassed them. That's what I think will happen to FreeCAD. FreeCAD is going to be better than all these other paid versions because there are enough people in the world who do not want to be paying rent on free on software. So without having any projects ongoing, I keep bringing warnings. It just keep bringing warnings for me like a virus. I don't understand it. Okay, what I'm going to do for the next 20 minutes that we have, I'm going to go through I will send you the web page after the class where somebody tried to show you how to do assembly. He tried. I found that his assembly is far simpler than the kind of things I try to assemble. But I saw that there is a pedagogical value in what he did because when the objects are very simple, you can concentrate on the theory of the assembly itself. Whereas in my own case, you are going to be bothered about getting the drawings right. But these drawings, they are just so dirt cheap, so easy. So I decided to do that same thing. I tried to do that same thing for you. So you will get my own file so that anywhere you are stuck, you can go and check in my own file. So if you get stuck, go check my file and then learn what to do. So even the sketch, I took you through the sketch step by step. Even every line drawn there, I took you. So I want to see whether that helps to bring, I want to use this to bring everybody on board because there is no reason why anybody should not do well in this course. I want you to do well in the course and I want it to be the beginning of proper engineering training in your life because anything you are going to do in engineering, you must be able to define it graphically. So let us go to the next slide. It's the next set of slides. Let's see, that is step 2. So let me close this and I want to do a slide projection. It's a slide show from the beginning. Okay, so you are going to get this set of slides in addition to the ones we just covered. So make sure you have installed FreeCAD 1.1.0 RC2 release candidate 2. Things change fast and furious in FreeCAD. You get stuck in online videos partly because of an unstable environment and version issues. The drawing I'm talking about here takes only 15 minutes. And that is, I timed myself when I did the drawing. It took me 15 minutes, but if it takes you 30 minutes or 45, don't blame yourself. I've been doing this thing for a long time. So after some time, you will be faster than me. So don't worry. You start slow, but you are going to get there. You could go in circles because of wrong version and unstable releases. The version 1.1.0 RC2 is not perfect. In fact, I've already seen some instability and bugs, but it is likely to do the job. So this guy did an assembly of an internal combustion engine, the one I showed you before. A small one, not as good as the one I did in Fusion, but it is very good and I'm quite happy with it. That's why I took the trouble to do it all on my own, followed these specifications. But as I followed the specifications, I saw that it's giving some instructions that might not be easy to carry out. So I changed those things. So the step by step is you create a document. I call mine class demo 001. So you create a document, add a body to it. Uh, Let me know in the chat room if there's any point that you can't do. You can just set up your free card, create a document, and name the document. And then you add a name to the body. I call the body skeleton because that's what it's going to be. Create a new sketch for this body and rename the sketch master sketch. So the model tree, instead of unnamed body and origin, you now have class demo 001, skeleton and origin. Class demo because you name the file, skeleton because you change the name. If you right click on the body, you see what I have here. If you right click on the body, it will bring this drop down menu and you go all the way down to rename. When you press rename, it allows you to rename the name of the body and you call it skeleton. Whereas if you change it, if you save the file and you give it a name, that's what you see here. If you if you rename the body skeleton, that's what you see here. So when you right click the body, you go to select rename and it gives you. So I believe everybody can do that. Now, the first thing you do is that you draw a slot. You draw a slot. A slot is one of the top menus in when you in your after once you say create a sketch, you choose the XY plane, and you now, as you are creating your sketch, you can bring in a slot. If you take the slot, uh, I think I have, let me see. Last time I tried to do this in class, my internet wasn't fast enough and I didn't like it. Let me just go through it. If we have time at the end, I might just do some of it for you. So you choose the slot. The first thing is that you make sure you are on this line and you will see a sign that you're on the line. You will see a curve with a dot on it. That shows you are on the line. And then you start on the line and you go down and you stay on the line. And then you give the parameters 110 and 15 for I think it's 15 for the width of that. So when you do that, you have this, and and then by the time you do, in the two eyes of the slot, you make a circle of radius 7 and another circle of radius of diameter 10 here. Once you do that, you can see that everything here is turning green. And you'll be thinking, I didn't cheat, I didn't cook it. It actually turned green. So, so if you follow the example and you want this thing to be symmetrical along the along the x-axis, so you make this distance 55, make this 110, or you select the 2 points and then select this one and say that should be, and this line should be a line of symmetry. So you have objects here, this object, this object, this object. So choose the slot object and then height 110, make it symmetrical about the x-axis, and you are having these slides and you are having the file where the thing has been done. So use those two to get yourself up to steam. Everything should turn green as you can create two center circles radii 7 and 10 on the eyes of the slot. When you do that, the next thing you are going to do is that you are going to take a 3-point, you are going to go to the arcs. You take a 3-point arc, you click something near it on the left, you click another thing near it on the right, and you click something below, it will get this 3-point arc. You do another 3-point arc on top here, click here, and click somewhere in the middle, and you get the 3-point arcs. So you have two 3-point arcs. Then the next thing you do, just join the ends with straight lines. You join the end with straight lines. what you are going to do, uh, make the lower radius 17, the radius of the one below 17, the radius of the one above 25. Then these lines be tangents. Let this line be tangent to this and be tangent to this. Let this line be tangent to this and be tangent to this. So let the lines become tangents. And then you force the center, you force the lower center to be in the eye. So you force this center to be here. How do you do that? You mark the 2 points. You make sure you mark the 2 points and you go and click. You go and click coincident. Once you click coincident, it forces it. Then the higher one, what you do for with that is that you force the line, you force it to be along the y-axis. When you do those two, everything becomes symmetrized. Everything is symmetrical, and then you make the distance between the two centers 30, and then you get something like this after you have done all of that. So the next thing you do is that you do a second slot. When you do a second slot, the second slot is coming, it is going to start at this point here. And when you start it at that point, at the point 0 minus 15, that is at on y-axis, and y is equal to minus 15. So you start it from here, and it is 75 by 15, and you make sure that the lower part is removed so that it is straight there. Once you make it straight here, no matter what method you use, you will lose all the dimensions and constraints. So you have to put them back. I don't know why FreeCAD behaves like that. You have to put them back again. So this is this one, make this 30, make this 75, and make the radius there 15. That's it. So the next thing you do, polyline and rectangle. You 3 perpendicular lines from coordinates minus 30, 20, which is this point. 1 line, 2 lines, 3 lines to 30, 20, to 30, 20. Let them be symmetrical about the y-axis. All you do is that after making these 2 lines vertical, you take this point, and take this line, and you ask for symmetry, so it will be symmetrical. And then you also use the equality constraint. Let this line, and this line, let all those 3 lines be equal, and make one of them 60. Once you make one of them 60, all of them will be 60. If you change this line length, everything will change. And then you fully constrain everything. Again, everything is green. The next thing you do is that you want to draw this rectangle here. You want to draw this rectangle. And what do you want to do? You want to start the rectangle at the middle point of this line. What you do, just hover your mouse around there, and you will see something that will show you are the middle point. Click it. You see the symmetry issue, that if you click it, you will see that this side is equal to this side. You take it from there, go 4 units to the left, 75 units up, 4 units back, and close it up. So, or just use a rectangle. If it's a rectangle you are using, just take this point and take this point, and your rectangle is cooked, and that's it. So this is the master sketch that will do what that video I'm giving you is asking you to do. So if the guy there, he speaks so fast, and I don't know how many people can follow. So I have followed him and I've done it. So you go try it and make sure that you actually practice this, because I've broken it into simple steps for you to do. So when you finish and you say you are okay, you now go again, and that sketch you created, you are going to right click on it, and you are going to click rename, and you are going to call it master sketch, and you have it like this. It's because it's on the XY plane. So from that master sketch, you can make 7 bodies. These bodies will each have their own sketches. The crux of the matter here is that the bodies will be built of sketches connected to the master sketch. The key connection here, as you will see, is the shape binder. Remain in the part design workbench, stay on the top menu and select new body. If you select a new body, control and select the new body and the master sketch. When you select both the new body and the master sketch, in the part menu, you can choose the shape builder. It's not shape builder, sorry, it's shape binder. That's my spelling error here. Shape binder. A new shape binder will now add to your new body. So when that happens, you name the new body cylinder. I will show you how this plays out. Choose the cylinder as the active body and double click to make it bold. Create a new shape binder under the cylinder by selecting both the cylinder and the master cylinder. I'm just repeating myself. With the two highlighted, select the shape binder under part design. A new shape binder is created under the cylinder on the model tree. So you turn off the master sketch. If you turn off the master sketch, you will still see the drawing. Even after you have turned it off, it's as if it turned orange. So the shape, the master sketch is gone. It is the shape binder that is orange on the same plane. So it shows in orange because of the shape binder. So the next thing you are going to do, you now create a sketch inside that object. And then you use projection or intersection, brings in objects from the shape binder into the project. After selecting what you need, you may close the eye of the shape binder. In other design, you may add more elements to this sketch after bringing some to the shape binder. Note that modifications to the shape master sketch will be automatically reflected. So once you do that, once you do what I've just told you to do, this is the only drawing you have now. This is the only drawing, and you copy that drawing, you projected it from the master sketch. If you now, at that point, if you now choose to do a simple revolution, you are going to get this. Okay. In the same way, you can create, like you know how we created skeleton, you know how we created the cylinder. You can create all the other things from just taking parts of the drawing and making a simple extrusion. You can create all the other bodies. We create other bodies in the same way and obtain, in addition to the cylinder, the listed bodies on the right. Don't worry, the guy in Mango Jelly, that is the name of the people that are doing this video, they explain these things, but I'm hoping that by the time you take their explanation and you add it to my own explanation, you will be able to marry the two and get something out of it. So where you don't hear them, you hear me. Why I'm confusing you, maybe they are clearer. Okay, the assembly. You can now move to the assembly workbench. No, I don't think you can even still move to the assembly workbench yet. Because the next thing to do is to create parts. Let me see. You make parts. Use this icon. You use this icon to make parts. So go to the in the part design. It's not part workbench. Part design workbench. You see this icon. Once you create it, you will be able to make parts. So what you are going to do, you drag each of the things you have created into the part. You drag each one into new part, and new parts will be created. You get a list of parts like this. You can now move to the assembly workbench, create a new assembly. You will see all the parts that are ready for assembly. Note you can select as many copies as you want. And then you are going to, it's when we finish assembly that it will become something like this. I can still work further on this. These are the parts you have created. What I want you to know is that you cannot assemble bodies. You cannot even assemble parts. You can only assemble components. Components are instances of parts. So when a part, for instance, if a part here is, say, con rod, that means that you can bring 10 con rods into your drawing. They will all be exactly the same. And so you can assemble them together because those con rods are components, but the con rod template itself is called a part. Those are the things. When you are assembling, it is only it's only this thing you can see. Let me see whether in the 5 minutes remaining, whether there's anything we can still do. Let me just go to free card and see whether there's anything we can do. So let us start a brand new document or clear all. Save the changes. Yeah, I don't think you need to. Okay, if you clear all, what I'm saying here is that you create a new document, and the document is unnamed. And then after you created a new document, the next thing you want to do is to add, if you are still in the part design, you can bring this one down uh, and say add body. Sorry, create a new document, new body. So when you have the new body, this thing is disturbing me here. Let's see whether I can move it away. Okay, new body. So you can save your file. If you save your file, you save your file as whatever you name you want. So it goes bring your hard disk or your drive and whatever name you call it here, that will be the name. Okay, let us say whatever name you put there will be the name of your top menu inside your model tree. So that is whatever name. Then you want to call this one skeleton, you right click on it and you go to rename, and then you can now call it skeleton. Okay, once you do that, you now begin a sketch. You begin a sketch. This is how you create your master sketch. You create your master sketch by beginning a sketch here. And I said you should start with a slot. You take your slot here. Now you come here. When you see at this point, you see something like that that shows that we are on the y-axis. You click there and you go back, you go down again. And once you are sure we're on the y-axis, you click again. So we'll make that 30, or no, 30 is too much. So let us make that 15. And then let the height, okay. It hasn't given me the height. So I can go to the dimension tool here and I can make this height 110. 10. Oh, it didn't succeed. Let me change this. Edit value. I want 110. Okay. So it's 110, so we can choose to see everything. So it's still not grain. So there are two ways to make it symmetrical about here. I can choose this point, then choose this point, then choose this axis, and then say that everything should be symmetrical about that axis. Put the symmetrical constraint. Well, it is saying wrong selection. These are the kind of problems you have. So if I can't do it that way, there's another way I can do it. I can just take this, I can just take the dimension. I can just take the dimension of this line that is from here to the origin on the straight axis. I can make it 55. My computer is slow. I hope you are still seeing the thing here. It is exceedingly slow now. I don't know why my internet is so slow today. Wow. Lost everything. So I don't know. This is interesting. Well, our time is done, so I don't want to keep you any further. You will see, I will send you what I've done, and then you will be able to do whatever you can with it. Please be ready for next lecture with everything that I've given you so that we can move on and finish this up in the next lecture. Thank you.